changes.
Wait, changes. What changes?
From one to the next.
Oh, hang on.
Ernie. And
I think this might help. I predicted somebody would eventually talk about the distance between the points.
Oh.
So, I think I'm gonna erase this too. I'm sorry, it's right on my head. Sorry, Hamish. So, where did you get that 2.5 from, Eric?
The 8081 is 1, the next one's 2, the next one's 4, the next one's 3, which is 10 divided by, actually divided by 4, but there are 5 points, so I should have divided it by 5.
Wait, do that for me again. I didn't quite follow. From here to here?
Is 1, and then...
Oh, I see,
Yeah.
I see. Okay, so this, I see how I was thinking the same thing, like, how do you get 2.5? When you described what you were talking about, I got 1.2. And that's because you did them in the order they came here.
Right.
And I did them in the order I placed them on the number line down here.
Okay.
So I'm removing the order from the idea, if that's okay with you.
Sure.
So, and again, I want to make this as general as we can. I don't want to say this was the first, second, third, fourth, and fifth. And if I do that, it assumes there's meaning between first and second. As you say, midterm, final. I don't want to have that kind of definitional thing in there. I want it to just be an exam, another exam, unordered. But let's do what you just did. So what you're saying is, this distance here is 1. This distance here is also 1. This distance here is 1. This distance here is 1. So they're just 1 apart. So you averaged them, is that correct?
Yeah.
And then you came up with 1, right? We could also, if you want, tell me if you like this idea or not. We could also say, well, the distance here is 2. The distance here is 2. The distance here is 2. The distance here is 3. This is also 3. The distance here is 4. Maybe we should average all of those, which I think is going to be close to probably 2.5. That's getting a little ridiculous. Is that getting ridiculous? Okay, let's sorry. Let's just go with Eric's. Let's just go with Eric's. Can we do something similar with Bert?
Yeah.
So if we do it this way, we get an average of 1, yes?
Uh-huh.
Fair. Good. How about up here? Bert's here. Okay, what's the distance here? That's 7. 7 points, yeah. And then we got 68 up to, looks like 82, is that 14? I think I did that right.
Yeah.
And then this up to 94 is going to be 12. And then 94 to 100 is going to be 6. So on average there, 21, 18, 39 divided by 4. I'm going to make it 40 just to make it easy and call it 10. Oh, divided by 3, call it 13. There's 3 distances, right? Oh, there's 4 distances, so we'll call it 10. So I'm ballparking the number here. So I'm calling that 10, and I'm calling Ernie's 1.
Right.
So what we've just done is we've assigned a number of variance to the 2 guys. So number 1, Ernie is a 1, Bert is a 10. Does that make sense if we're trying to apply a measure of variation, that a larger number should imply what? More change, more deviation. Does that make sense intuitively to us? Yeah. Good. Let's write that down because that is true for all statisticians. They've agreed on that. You got to realize, we're developing formulas in this class. We're developing ideas in this class that are not like natural laws. The idea of variation isn't quantified in nature. Nature just says, here you go bees, go make honey. Here you go bears, go poop in the woods. Nature just does. The world just does. We try to understand it by putting quantitative measures on it. So we have to make up our own measures for it. So what you guys just did was, you now have a gut feeling, I'm going to put it in orange up here. You have a gut feeling for what variation should be, okay? So sets, or let's put data sets. Data sets with larger, I'm going to put larger in quotes, if that's okay with you guys, because we haven't really defined what large means yet, have we? With larger variation, should have a greater dispersion number. I'm going to call it that for lack of a better term. A greater dispersion number than data sets with smaller variation. Oh, that's good. That's good. I like that. Hopefully that makes sense. So Bert should have, Chris, tell me what's on your mind. You don't buy that. You don't buy that. Go ahead, tell me.
Oh no, I'm just trying to, is this like going into standard deviations?
We're shooting towards that kind of an idea.
Okay.
How many of you have heard of the term standard deviation before? Standard deviation, maybe a third of you, maybe only a quarter of you. Yeah, that is one measure. That is one measure. We haven't defined it yet. We've got what's called the Eric deviation, which I like a lot, actually. Because he's given us a number, we're going to call it the E number, E, that says Bert is 10 times as EE as Ernie is. 10 times as EE as Ernie is. I like that very much. I like that very much. Any other ideas? Does that orange statement make sense? Does it sit okay in your gut? So Chrissy, you weren't actually frowning at that statement. You were just kind of like making the connection between that and what you had already heard of before.
Yeah.
Good, and doesn't it also hold to what you've heard before?
Right.
Good, connection made. Excellent, check. Bing. So, larger numbers equals more variance. Anybody got a problem with Eric's measure? I don't. I think it's great. I also, unfortunately, nobody uses it. That's the problem. Nobody uses this measure. I don't know why. It's a nice one. It's a really nice one. I think it might be because of the arbitrary... Remember how upset you guys were getting when I started... Let me put the camera back over. Yes, thank you, Katie, for looking at that. That's good.